So here we go. Back here first. So you have this, here, this. All right, so 10 volts this way, 12 volt this way, 1 amp this way, and 2 volt this way. The question is, what is the current entering in the gray resistor, which is this one? So let's go for it. So let's put a bit of color and call the current here I. Okay. And you know that this resistor, all the resistor equals to 1 ohm, so they are all R, and R equals to 1 ohms, correct? So the idea is what? To find this current here. So to get this current also, so you have few options. First, you can try to check if you get something from the circuit. So you're interested in this voltage in between these two terminals. So let's call it UR. Do you have any information on this UR here? In fact, you see that all the stop node here are the same, correct? Here, be careful because this is not the case. These here are the same, but not this one. So at the end, you can tell that these, sorry, I'm going to change color. I have to fix this problem of pointer. So this node is the same than this node. This node here is the same than this node here. So in fact, this 10 volts here is applied between A and B, correct? So in fact, you have this 10 volts in between the terminal of your gray resistor. 10 volts are like this. You're interested in this current I. So if you plot UR like this, you can tell that UR equals to minus 10 volts, correct? So you can deduce that the current you fix in this direction equals to minus 10 amp. So UR is, sorry, R time I. R is always positive and is 1 ohm. So the current is minus 10 amp. Do you get that?
Yes, thank you.
Okay. So in all these quick circuits, before starting applying mesh law, node law, etc., try to see if the circuit could be simplified, or if you already see some shortcut or maybe already values you can play with. Okay. Someone else with a questions or a concept or something you want me to recap, to detail or Describe.
Yes.
Yes.
I did not succeed to do the fourth circuit of the exercise 3 that we had to do.
This one.
Yes.
Okay. So from here, so do you agree with how I can get all this formula?
Yes.
Do you agree with this formula? Okay, perfect. So then let's try to apply Ohm law. So UR1 here equals to R1 I1 equals to R2 I2 equals to R3 I3. Okay. So then from here you can deduce I1 as a function of I2, I1 as a function of I3. So I1 equals to R3 R1 I3. Oops, sorry. So if it's a 2 here, it's a 2 there. Same thing if it's R3 R1 I3. Okay. So then you can put all this form. So you can say, okay, now you have I1 as a function of I2, I1 as a function of I3. You can keep going and write I2 as a function of I1. So you have I2 equals to R1, R2, I1. I3 function, sorry, I2 as a function of I3, which is I2, R3, R2, I2. Okay, so it's all the expression here. Then you can substitute in the main first one. So let's say that each time you want your result being I don't know, you want the result about I1. So you want all this first equation as a function of I1. So in fact, you want I2 as a function of I1. So you're going to use this formula. And then you want I3 as a function of I1. So I3 as a function of I1 is R1 3 I1, correct? So then you get this main expression as a function of I1 and I, and you should go back to this formula. Is it clear?
Yes, thank you.
Perfect. Other questions? No questions?
It's fine, thank you.
We good? So if there is no more questions, let's keep going in our exercises. So from now you have all in your hands to work more or less on your own on the exercise from the next next part. So let me grab the exercise document and we start with exercise 4. First one, quite simple. You have a single mesh circuit So you have R1, R3, R2, I1, sorry, E1 and E2. And I'm gonna just change color. And this is the current. And we ask for the value of this current in this circuit. So the same protocol every time. I'm gonna repeat this again, and again, but here you are in front of a single mesh circuit, so it's quite easy to handle. The current is already fixed with a fixed direction. Then you have to label every voltages in between the terminal of your dipole, which means that you have to label the voltages in between the resistor R1, R2, and R3. You select the convention you want when you draw these voltages. I'm going to use the receptor convention. So I'm going to call this UR3. I'm going to call this UR2. And I'm going to call this UR1. As you can see, each time I picked the receptor convention, because if you keep following the, do you see my arrow here? The arrow of my,
No, we don't.
oh, sorry.
I-
Okay, I have to see how I can do this. Okay, sorry. Next time I will try to make this clear. So the current is going in that direction. So each time I'm entering in one resistor, I'm going in the opposite direction than the voltage I'm plotting. So from now, everything is labeled on my circuits. There is no node, so there is no node law. The only thing now you have to apply is the mesh law. So you start from whatever point of the circuit you want. You can pick this corner. Then you fix a direction saying, okay, I'm gonna apply the mesh law, considering that when I go from here to here, I will see how the voltages are. And if they are in the same direction, then this arrow here, which means in this direction, then I will put a plus in front of it. So I'm gonna do this with you right now. So let's start from this node here and we go. Here we face this UR3, which is in the opposite direction. Remember, we go in this way. So it's minus UR3. Then keep going. I face E2 in the opposite direction. Same thing for UR2. But now E1 is in the correct, well, not in the correct, but in the same direction that I pick, then I face UR1 in the opposite direction. And this is the mesh law I apply from this node going in this direction, point by point. Is it okay for everyone, or do you want me to summarize this or maybe slow down?
It's clear for me.
Okay, no question?
No questions.
Okay, perfect. So here, because I picked the receptor convention, I already know that all the voltages are going to be positive, which means that UR3 equals to R3I. E2 is E2. This is R2I plus E1 minus R1I equals to 0. And I'm done. Okay, then the question is, what about the current I? So you have I as a factor of R2 plus R3 plus R1 equals to E2 minus I1, and you deduce that the current equals to I1 minus I2 over all the R. Done. Quite easy because, well, from now, there is not a lot of options you can use. You only know the node law, the mesh law, and as I said previously, as soon as you label the circuits and you know the convention you use, you are good with 80% of the job, then it's only math. Just to explain that again, this is a convention I use. I'm gonna, so you have this result somewhere, but now let's say that I won't use the mesh law in this direction. I'm gonna use this in the other direction. Just to show you that we're gonna end up with the same results, whatever convention you pick, but let me demonstrate this for you. So remember, it's I1 minus I2 over the sum of the R. Back up here. Instead of going in this direction, I'm gonna go in the other direction, saying it's positive. One thing you can also do, if you want to make the, the circuits more complex, I don't know, it's again picking a direction, and instead of saying that it's going to be a positive sign, of course you can say it's going to be a negative sign. I don't know if it's useful, but again, it's a convention. So I'm going to still start from this node, go this time in this direction, and again see for each voltage I encounter if it's in the same direction that the law I use. So let's start from here. I go with UR1, which is in the same direction, which is not the case of minus E1 plus UR2 plus E2 plus UR3 equals to 0. Then here I equals to R2 plus R3 equals to I1 minus I2, and you get the same result. So I pick another convention, but again, I found the same result. Let me show you another convention. Instead of using the receptor convention, I'm gonna pick the generator convention. So back again here, and I'm gonna rewrite all these voltages here. So this one is so this is I2. So now, instead of using receptor convention, I'm going for the generator convention. So I'm labeling correspondingly all these voltages in between the terminal of my resistor in the receptor convention, in the generator, sorry, convention. Again, I'm gonna apply the mesh law, going that this is gonna be positive in this direction, starting from this node, going this way. So I get UR3 minus E2 plus UR2 plus E1 plus UR1 equals to 0. Now, since I'm using the generator convention, I know that all the voltages between the terminal of the resistor are going to be negative. So minus R3I minus E2 minus R2I plus E1 minus R1I equals to 0. And again, you find the same result, I1 as a function of sum of the R equals to minus E plus E2, and you get the final result. Is it clear for everybody? Because this is quite important, this convention thing and the mesh law, the way we apply it in a single mesh circuit for now.
For me, it's clear.
Okay, no questions? We can spend some time. Well, here it's really important for you to catch this, because this is the single source of mistakes from now is this convention thing and applying the mesh law in the wrong way. No problem? So this is your turn now, and you go for the next circuit. So next circuit, I'm just drawing the circuit here. The question is a bit different since we are looking for a voltages between 2 points. So this is E1, this is E2, R, 3R, and R. The question is, what is the voltages UAB? Which means this voltages, it's already fixed because I fixed the name UAB, which means the voltage is pointing toward the first layer. So you need this voltage. Know that this UAB voltage is going to be partially E2, but then you need the voltage here. The voltage into the terminal of R. To get it, you need the current in this mesh. So again, you start with this single mesh circuit. You have to label everything. Here, in that case, the current is not labeled. So you label it, keep this direction, then you label every voltage in between the terminal of your resistor, and you go for the mesh law. And I'm waiting for you to work and for the solution that I will write in 2 minutes. If you have questions, of course, feel free to let me know if something is not clear. If you already have the result, please keep going. This is the answers of question B. The answers for question C is yes and no. So it should be quite easy to get. Do you have any issues finding the UAB result? Or is
For the first part or the second part of the exercise?
or yeah, for now just the answer UAB.
Yes. It was
Okay.
simple.
Is everyone okay with finding the result of UAB, or are you still in the processing of finding the equation?
I'm still doing it.
Okay. Then you can think about the last question. This is about you are in a single mesh circuit, which means that the current flowing through this mesh is unique, which means that in fact, if you consider resistors in this mesh, they're all in series. Then the question is, could we simplify these three resistors into a single one? And is it going to change the final result? So for the first circuit, the answer is yes, you can simplify them. And in the second circuit, the question is no, you can't. Just leave you an extra minute. And then we move to the double mesh circuit.
Sorry, why
Yes.
is it not possible in circuit 2? Can't we do R plus 3R?
Okay, so in the circuit 2, the thing is you are not interested in the current. You're interested in a specific voltage. So, which means that to get the value of the current in this circuit, of course, you can simplify the three resistor. So this result here is equivalent to actually this. Do you agree? You can just slide, you're in a single mesh, you can slide the components along your wires. You see that the two voltage sources are in the same direction, so you can add them. Then you end up with this, correct? So from here, it's quite simple to get the current flowing in this mesh, which is E1 plus E2 equals to 5R times I, which is I equals to E1 plus E2 over 5R. This is something you should have found. So then the question is, what about the voltages here? In between these 2 points, where it's already fixed that you have a resistor and you have another voltage generator. If you start simplifying your circuit, like what I did here, then you have changed everything, because now maybe A and B is here, you see? So now the voltage you consider between A and B is 0, which is not correct. So when you discuss currents in a single mesh, then you see that all the things are in series. So this is not a problem simplifying your single mesh circuit. But then when it is asked for a specific voltage between 2 points and you have components between these 2 points, then you are not allowed to play with this component. If not, you of course are changing the voltage in between the two terminals. Is it clear?
Yes.
So you can go for the simplification of the resistor here, associated them to get the final current, because now you know that the current flowing through this circuit is in this direction, I, and get this value. But now back to what is the question, which is the voltage UAB, then you know that UAB equals to minus UR plus E2. Minus UR is R time, well, it's, sorry, minus E1 minus E2 over 5 plus E2, and you get back to this result. Okay? And we're done. Is it clear for everyone?
How do we know that R is equal to minus E1 minus E2 over 5?
UR here is, if you go back to the circuit here, UR is, sorry, UR is R time I. Receptor convention. Sorry, I'm gonna just change color.
Yes, okay.
Receptor convention, R, UR equals to R time I. It's negative because when you just check for the vectors for the direction of UAB, you see that UAB is minus UR plus E2, and you get the final result just below.
Okay, thank you. And also, I thought I understood, but I always get the signs wrong.
When you apply the receptor convention or when you apply the mesh law?
Both.
Okay, so don't forget, receptor conventions mean first, if the current is fixed, then the current flow in a specific direction, then you have to pick, if you are in the receptor convention, the voltage in the opposite direction. If you do so, then you can say that the voltages is positive. It's R time I. Okay? So then you are discussing the mesh law. Mesh law is just a sum of vectors. If you start from one point and you go back to this same point here. So let's call this point D here. And let's go for the mesh law in this direction. So I already label the current here like this, which is like this, which is like this. Then you have to plot the voltages using receptor convention in the opposite direction than the current. This is UR, this is U3R, and this is also UR. Then you start from here, D, and you go in this direction, saying, okay, I'm gonna flow in this direction and say everything I encounter in this direction is considered as positive. So first you face E1, same direction, so it's plus. Then you face UR, opposite direction, minus UR. Then you face minus 3R, you face U3R in the opposite direction, so it's a minus. E2 is in the same direction. Then you keep flowing in this way, and you face UR, which is in the opposite direction. And then you end up at D. So you end up with your mesh law equals to 0. And then the only things you have to do is to substitute all the voltages here by R times I because of the receptor convention you use. But you keep, of course, the minus sign in front of it. And then again, you should find the same result. Okay? Is it better?
Yes, thank you.
Perfect. So let's move to, except if you have some questions, we move to the double mesh circuits. Here we go. First, so you have this, here we go, another resistor here, another resistor there, here we go, E, R2, R3. The question is, what is UAB voltages? So you have A here, you have B there, so UAB is only in this direction. Be careful because this is a common mistakes you're doing in exam. We ask for UAB, so this is the only way of plotting UAB. Always pointing towards the first letter. So to get UAB, something which is going to be interesting, of course, is to get the current flowing into R3, because you already know that U R3, which is UAB, is going to be equals to R times I. R3, sorry, times I. Okay, but you don't know the value of the current. And you are going to start this circuit, as always, by labeling currents and voltages. I already fixed the currents I in this direction. Why? Again, to get the receptor convention, since UAB is already fixed. Then, of course, you are gonna flow your current. This is I, this is I. I'm still in the same branch here, but then I'm meeting here node, here and here, which means that the current is gonna be divided into two. One flowing into R1 and another one flowing in the branch of the voltage generator. So let's call this guy, I don't know, whatever you want. In the direction, again, you want. Let's say that this, I'm going to call it I1. And of course, you can say, okay, this is also I2. But you can simplify your life and already apply the node law here. You have I1 entering in this node that I'm going to call C. So you have the current I here, another I1 going out from here. So what is the value of the current going upstream here in this direction? I'm listening.
I minus I1.
I minus I1. Brilliant. And you respect the node law. I entering equals to the currents going out from the node, which is this plus this. Okay, so now currents are labeled. Let's go for voltages. This UAB voltages is already labeled. I'm gonna label all other voltages in the receptor convention. Again, this is your pick. If you want to use a generator convention, this is fine. And then you are done with the labeling and 80% of the job. You already apply the node law here in C. Of course, you can apply it in D, but this is useless because you already know that so you have the current I1 flowing here, I1 is flowing there, then here you have I minus I1 here, and well, the node law is respected. So now your last option is to use mesh law. So what you're looking at is UAB. UAB is a function of the current, which is an unknown. So you have one unknown here as a current. The only other unknown you have introduced is the other current I1. So the two unknowns are I and I1. So you need two equations. Here you have the so-called double mesh circuits, but in fact, you have three meshes you can play with, which is going to end up with three equations. Three meshes because you have these meshes here, you have another small meshes here, and you have a large global meshes. So apply the mesh law in two of these three meshes, then you're gonna end up with a system of two equations with two unknowns that you have to solve to get your final result. Let's go. If you are done with the circuit number 1, go for the circuit number 2 and the circuit number 3. Always the same protocol. You label, if it's not already done, the current and the voltages. when you label the current, you apply the node law straightforward, so you already simplify your life. If not, it's gonna be more complex to solve for you. And then you apply mesh law. So this is UAB for circuit 1. UAB for circuit 2 is R1, R3. I over R1 plus R2 plus R3. Circuits 2. And the last circuit is UAB R3E minus R3 I over R1 plus R3. If you have questions, feel free to ask them. If you're blocked at some point.
have a question.
Sure, go for it.
Are all of these values of UAB like equal to each other, or?
No, not at all. This is different circuit.
But okay, so, but with us, I mean, if we can find different things.
You shouldn't be finding different thing.
Okay, because I only find the first one, so but I don't know.
Yeah. I mean, if you're on the first circuit, of course, you should end up with only this first formula.
Oh, that's all the answers. Okay.
Yeah, that's already all the answers for all
Okay,
the
I thought that
circuits.
was for the first one. Okay.
No, sure,
Thank you.
no problem.
Excuse me. I don't understand the difference between, like, for example, in circuit 1 and in circuit 2, like E and I is just, yeah.
It's not the same thing. In the circuit 1, you have a voltage generator. In a circuit 2, you have a current generator. So it's a bit different, because if now I move to the second circuit, R1, R2, R3. You have a current generator, which means that in fact here the current in this branch is fixed and is equal to I. Then you reach the two node here. Of course, you can go for calling this current I1. Then you apply the node law and you go for calling this current correspondingly knowing the mesh law. Then you go for labeling every voltages in between the terminal. Something which is quite important, we will discuss this later, is here we have a current generator. It's written like this, which means that it's delivering a current in this branch, but this voltage generator do have also a voltage in between its terminal, and I'm gonna call UI. So this UI is an unknown. So one thing which is quite important to remember, and I will keep repeating this again, is when you have a current generator, do not apply the mesh law in a mesh including a current generator. Why? Because you already had an extra unknown, which is the voltage in between the terminal of the current generator. So here, you keep labeling the voltages. You know that the current flowing in this direction is is I minus I1. So you don't want to play with this branch, which include a current generator with an unknown voltage in between these terminals. So you're gonna only play with this mesh here, which is in fact enough, because what you are looking at is at the very end this UR3, because this is UAB. And for UR3, you need only I1, because this is R3 times I1, and I1 is an unknown. So you are going to play with this mesh here, apply the mesh law here to get the current I1 as a function of I, but I is known because it's delivered by the current generator. So you're done. Is it clear?
Yes, thank you.
Perfect. All right. We are good with today's class. I will leave you with these results so you can keep training you on circuits and find the different voltages in the different circuits. We meet, I think, on Friday morning. So feel free to drop me an email if you have some questions in between. And if you have no questions, I wish you a good day, and we will meet on Friday.
Okay.
Thank you.
Bye.
Thank you.
Okay.
Bye.
Goodbye.
Bye.